So now we're going to describe what the variant of this coordinate descent algorithm looks like in the case of lasso. Again, we're going to be looking at these normalized features. And just remember, this is where we left off with our coordinate descent algorithm for just least squares, unregularized regression. And remember, the key point was that we set W hat j equal to rho j, this correlation between our features and the residuals from a prediction, leaving j out of the model. Well, in the case of lasso, what we're going to do is how we set W hat j is going to depend on the value of our tuning parameter lambda and how that relates to this rho j correlation term. So in particular, if rho j is small, if it's in this minus lambda over 2 to lambda over 2 range, where again, what small means is determined by lambda, what we're going to do is we're going to set that W hat j exactly equal to 0. And here we see the sparsity of our solutions coming out directly here. But in contrast, if rho j is really large or on the flip side, very small, what that means is that the correlation is either very positive or very negative. Then we're going to include that feature in the model, just like we did in our least squares solution, but relative to our least squares solution, we're going to decrease the weight. So in the positive case, if we have a strong correlation rho j, instead of putting W hat j equal to rho j, we're going to set it equal to rho j minus lambda over 2. And on the negative side, we're going to add lambda over 2. So let's look at this function of how we're setting W hat j visually. Okay, well, this operation that we're performing here in these lasso updates is something that's called soft thresholding. And so let's just visualize this. And to do this, we're going to make a plot of rho j, that correlation we've been talking about, versus W hat j, our coefficient that we're setting. And remember, in the least squares solution, we set W hat j equal to rho j for least squares. And we can see that just setting lambda equal to 0. Remember, lambda equals 0 returns us to our least squares solution. So I'll specifically write least squares there. So that's why we get this line y equals x, this green line appearing here. So this represents, as a function of rho j, how we would set W hat j for least squares. And in contrast, this fuchsia line here we're showing is for lasso. And what we see is that in the range lambda over 2 or minus lambda over 2 to lambda over 2, if this correlation is within this range, meaning that there's not much of a relationship between our feature and the residuals from predictions without feature j in our model, we're just going to completely eliminate that feature. We're going to set its weight exactly equal to 0. But if we're outside that range, we're still going to include the feature in the model, but we're going to shrink the weight on that feature relative to the least square solution by an amount lambda over 2. So this is why it's called soft thresholding, and we're shrinking the solution everywhere, but we're strictly driving it to 0 from minus lambda over 2 to lambda over 2. And I just want to mention, to contrast with, let me choose a color that we don't have here. I guess red will work. I want to contrast with the ridge regression solution, where you can show, which we're not going to do here, but you can show that the ridge regression solution shrinks the coefficients everywhere, but never strictly to 0. So this is the line W hat ridge, and let me just write that this is W hat lasso. Okay, so here we get a very clear visualization of the difference between least squares, ridge, and lasso.